Hi everyone. Today, the topic we are going to see is annealing in wrought alloys. Okay. So, annealing as such is a very important topic when we are going to deal with wrought alloys in the field of dentistry. Okay. So, what are these wrought alloys? Okay, any metal which is cold work, okay, and has undergone plastic deformation, okay, to bring about certain changes in the shape of its structure as well as its mechanical properties, you call it as wrought alloys. Yes. So now, how these wrought alloys are made? You have to do some mechanical work and also you have to do heat treatment. So both together is going to give you a wrought alloy which is going to have a change in its structure as well as its properties. Yes. So now, where are these wrought alloys used in dentistry? It is used in various fields, like it's used as orthodontic wires, it's used as brackets, it's used as prefabricated crowns. Okay, you can also see it in partial denture clasps, endodontic files, also as surgical instruments. So these are the various fields where this wrought alloy is being used. Okay, so now how is this deformation brought about? How is it that deformation is brought about in the parent metal to bring about these wrought alloys? Okay, so what they do is they create lattice imperfections. And as a result of this lattice imperfections, you're going to have so many dislocation in their atomic structure. And as a result, it is going to undergo strain hardening. Okay, and ultimately you're going to get a wrought alloy. But say what happens if you're going to prolong this? If the strain hardening is prolonged beyond a certain limit, then what happens? Fracture of the metal occurs. Yes. So now this lattice imperfections, okay, which you are going to create in the metal to bring about this wrought alloy can be in the form of point defects or it can be in the form of light defects. Sorry, line defects. Okay. So when you talk about this point defects. Okay, so here you can see that in the structure there can either be a vacancy created or there can be some interstitial impurity created or it could be self-interstitial, okay, or just yes, sorry. So it could either be a vacancy or it could be some impurity or it could be some self-interstitial or some substitution in place of an atom or it could be a Frankel defect. So anything could occur, okay, anything could occur and could result in some point defect in that metal, metallic atomic structure. Okay. So then you have this line defects. So in the line defects, you can see that there is a edge dislocation which is taking place. So here you can see that in the figure on your right, you could see that the entire block has moved. There's an edge dislocation which has occurred. So this can also result in plastic deformation. Okay. So these are the two defects which could occur. Okay. Now, how do you bring about these defects? Be it a point defect or be it a line defect. So, how do you bring about these defects? It is by means of work hardening or strain hardening where you apply force, okay, or where you apply stress, okay. So, this you call it as a strain hardening or work hardening. And because of this strain hardening or work hardening, you are going to have the deformation of the metal which is going to take place. Okay. So in short, if you see, there is a dislocation, okay, which tends to build up at the boundaries of the grains. Okay, there is an atomic slip which is going to occur. Okay, and then you're going to have point defects also. And because of all these dislocations, be it point defect or line defect, your entire grain gets distorted, and as a result, you have a slip which is taking place in the atomic structure. And as a result, the metal deforms plastically. You get a newer metal, which you call it as a wrought metal, which is much more stronger, much more harder, and much more less ductile. The hardness, strength, everything increases, and the ductility decreases. But what happens when you do this cold work further, when you take this further, the material will fracture. Yes. So now, in short, strain hardening is going to bring about an increase in hardness, yield strength, and tensile strength. But however, the ductility and resistance to corrosion of the metal is going to decrease. Okay. So now you might wonder as to where this annealing fits into this. Okay, where does annealing fits into the strain hardening? Okay, so annealing is nothing but a process which you do to reverse this plastic deformation which has taken place in the metal. Okay, so what you do here is you just simply heat the wrought alloy to a particular elevated temperature, but you don't melt it. Okay, so as a result, the deformation which has taken place just gets reversed. So this is called annealing. In simpler terms, anything which is done to reverse the strain hardening which has taken place to bring about that wrought alloy, you call it as annealing, and you do it by simply heating it to an elevated temperature without melting. Okay. So now when you do this heating, what happens is the reversal takes place in three stages. Okay. So first is recovery, then there is recrystallization, and then there is grain growth. So these are the three stages in which this annealing is going to take place. Okay. So this stages of annealing, you can see this in this graphical representation where you can see this line is going to represent your tensile strength and this line is going to represent your ductility. And as you do annealing, I told you because of strain hardening, the ductility is going to decrease. But in annealing, the reverse is going to take place, which means the ductility will significantly increase, but whereas the strength of that metal is significantly decrease. So you can see that the metal has been cold worked, because of which the ductility has significantly decreased, the tensile strength is more. But when you do annealing, where it's going to occur in three stages, you're going to have a recovery, you're going to have recrystallization, and then you're going to have grain growth. So during the recovery stage, the tensile strength decreases, ductility increases, and during recrystallization, it significantly increases and decreases, and then it maintains itself during the grain growth. So this is what happens when you do annealing. Okay, so in short, this diagram will tell you if a metal has been annealed, you can see it becomes more flexible, it's more ductile, its hardness is decreasing. But whereas when you do strain hardening, its strength and tensile strength, its strength and hardness increases and its ductility decreases. So this figure will explain you what I told in all these previous slides. Yes. So we'll see about each stage in a very short, crisp manner. So if you talk about recovery, what happens here in this recovery stage is that the cold work properties will slowly begin to disappear. There is a slight increase in tensile strength, but ductility as such does not take a much important change here. And the microscopic structure is also not altered significantly. But whereas when you go to recrystallization, you can see that the older grains get replaced by new grains. The material becomes more ductile and the fibrous structure gets transformed into numerous small grains because recrystallization has to take place. So the bigger structure gets reformed into smaller grains. And now these grains have to grow in size. So that is called your grain growth. So in grain growth, you can see that the grain size increases, grains boundary as such decreases, though the size increases. Because of the increase in size, there's a significant decrease in the grain boundary. Okay, but however, the size that does not increase to an extent that you get a very big crystal. Okay, so instead it just stops once a relatively coarse grain structure is produced. Yes. So here, this diagram, if you see, you can see that this is a material microstructure of the material after cold working or strain hardening. But the same thing when you do annealing, you can see that the structure is entirely changed. You can see that there is recrystallization taking place and the recrystallized material has undergone grain growth. and this is more flexible and ductile. Yes. So again, this represents the same. You have a deformed structure with grain nucleation, which undergoes recrystallization, and then after recrystallization, it grows. Yes. So why do we do this annealing? Why is it that we have to do annealing? Because we want the material to have certain desired properties. So when we want to have certain desired properties, when we want to soften the metal, okay, when you want to increase its plastic deformation potential, or you want to stabilize the shape, you want to increase its machinability, you want to relieve all stresses, for all these you can do this annealing. So this annealing is otherwise called as hot working or quenching, stress relief. So all these are other terms. So you can call annealing as hot working or quenching or stress relief. So these are the various other words we use for the term annealing. But however, the same annealing, when we deal with direct filling golds, this term is used mainly to eliminate the contaminants from the surface of the gold metal. So that would be termed as annealing in the gold. Okay. So now I think you would have understood the basic concept as to what annealing is. So now we will see about a few questions which have been asked in the previous years in relation to this annealing. Okay, so the first question is stainless steel orthodontic wire can be hardened by or bending orthodontic wire at the room temperature. So what is it an example of? Okay, tempering, work or strain hardening, age hardening, precipitation hardening. So the answer is strain hardening. You do bending, you do all that to strain harden the metal. Okay. So the answer for this would be strain hardening. B. Next, second question, tempering of steel. So what happens when you temper the steel? Okay. So tempering is a stage where the metal is undergoing plastic deformation. The reversal of that is annealing. So here tempering is you are plastically deforming the metal. So what happens when you deform? Actually, it increases the toughness, it increases the hardness, it decreases ductility, it decreases its toughness. So the answer is it increases its toughness. Okay, so when you temper the steel, naturally the toughness of the steel is going to increase. Okay. Next is softening heat treatment. Softening heat treatment is what? It is nothing but annealing. So softening heat treatment, which is otherwise called annealing, will naturally increase what? It will increase ductility and not tensile strength or proportional limit or hardness. Okay. Next, the fourth question is heat hardening is a process done at. So what is heat hardening? Heat hardening is not annealing. Heat hardening you do mainly by heating it at 250 degrees Celsius, okay, for 15 to 30 minutes. So this heat hardening is a kind of tempering you do, and the answer for this is option C, which is 250 degrees Celsius for 15 to 30 minutes. Okay. So next, the fifth question is the rapid decrease in tensile strength and increase in ductility of the wrought metal is seen in which stage of annealing? Okay, so I hope you remember the graph which we discussed, where it is during the recrystallization stage or the second stage that there is a significant increase in the ductility. So the answer is B, recrystallization stage. Next, the sixth question is annealing is also known as. Annealing is definitely called as soft hardening treatment. Okay, so annealing is otherwise called as soft hardening treatment. Though option D is also a slightly correct answer, the most apt answer would be soft hardening treatment.